All right, today we're going to talk about implicit differentiation. And first we need to understand why we need a different type of differentiation. So first we're going to look at the difference between x minus 2y equals 6 and y equals 1 half x minus 3. Now these define the same function. If I solve this for y, I'd get that. But these are written in implicit and explicit forms, respectively. And that's great. Now, some functions can go back and forth. Now, some relations, though, we can't go back and forth so easily between y equals and non-y equals. So when a function is defined implicitly, it means that x and y are both part of the same equation. However, the equation is not or cannot be in y equals form. So what I should really have here is when a function or a relation is defined implicitly. So far we've only taken derivatives of functions that have been in y equals or f of x equals form. If a function's not in that form, again, or relation, then you can still differentiate. And here's how you're going to do it. Now, I'm going to skip over this for a second and refer back to it when I take the derivative down lower, and we'll come back to those steps. So let's say I have a circle. You're used to dealing with things that aren't functions. Circles aren't functions, but they're fine. They're helpful. We need to do calculus with them. So let's say I have x squared plus y squared equals 9. And I want to write it as a pair of functions because I really want it in function form. Well, that's fine. I've got y squared equals 9. What's happening here? I don't know what just happened. So I have y squared equals 9 minus x squared. And then if I solve for y, I have y equals plus or minus the square root of 9 minus x squared, right? So that's really not a big deal. And if I want to label the graph with each, then this would be the positive square root 9 minus x squared, and then this would be the negative square root of 9 minus x squared. And that's all fine and dandy. And if I want to take the derivative, that's also okay. So if I take the derivative of the positive square root, I'd have dy dx equals 1 half 9 minus x squared to the negative 1 half times negative 2x. Kind of begging to be simplified here, so I have negative x over the square root of 9 minus x squared. And if I take the derivative of the negative guy, dy dx, I'd have negative 1 half 9 minus x squared to the negative 1 half times negative 2x. And then those guys cancel, and I have x over the square root of 9 minus x squared. So dy dx can technically equal either of these things, depending on which half of the circle I'm really talking about. So fine, no big deal there. Now, here's where I get down to the implicit. Let's say I didn't want to solve for y, and I wanted to take the base standard form, x squared, x squared plus y squared equals 9, and I want to take the derivative. Well, step 1 up high that you can't really see right now, but step 1 up here says differentiate both sides with respect to x. Here's how we do that. I'm going to take the derivative of this stuff with respect to x, and then I'm going to take the derivative of this with respect to x. The derivative of x squared is exactly what you want it to be. It's 2x. The derivative of y squared is different. Y is dependent upon x. Y is still my dependent variable. So when I go to take the derivative of y squared, I have 2y times dy dx. What I really did was I did the chain rule. Bring down the power, reduce it by 1, take the derivative of the inside. And then the derivative of 9 is 0. So, step 1, differentiate both sides with respect to x. Step 2, get dy dx all by itself on one side. So if I do that, and I get the dy dx term all by itself on one side, I'm going to have 2y dy dx equals negative 2x. I think step 3 says factor out dy dx. I don't really need to do that. I just need to basically identify that these are separate pieces in this case. And then I'm going to solve for dy dx by dividing both sides by 2y. And I'm going to get dy dx equals negative x over y. So there's my derivative. It has an x in it and it has a y in it. I'm good to go. Now, does this match? Does this equal that? Well, yeah, it does. Because this says x, or negative x, over the square root of 9 minus x squared. And look, y is the square root of 9 minus x squared, so I have x over y. Now this plus or minus is taken care of with the fact that depending on if y is positive or negative, I will get that plus or minus in this fraction. All right, and then last but not least, I have used the implicit derivative to find an equation of a tangent line. Well, if I need a tangent line, I need an x and I need a y. So it says the tangent line to the circle in the first quadrant. So if I take x squared plus y squared equals 9, plug in 1 for x, I get y equals plus or minus the square root of 8. And if I want to be in the first quadrant only, I'm going to deal with the positive value. And if I reduce it, it's 2 root 2. So there's a y. There's an x. Now I need a slope. So I'm going to use my derivative, dy dx equals negative x over y, which in this case is going to be negative 1 over 2 root 2. So there's my slope. Y, x, slope, the three pieces I need. Y minus y1 equals m x minus x1. And there's the equation of my tangent line. All right, so I'm 6 minutes in. All right, jumping ahead. Let's say I get this curve. This, I believe, is called the Witch of Agnesi. Don't quote me on that, but I'm pretty sure this or things of this form are called the Witch of Agnesi. I think it's because it looks like a witch's hat. But a bunch of mathematicians a long time ago studied this and just dealt with this relation, okay? So this curve has this equation. Can this be written in y equals form? Not easily. I'm going to say it that way. Maybe not at all, but definitely not easily. I could break it up into a bunch of pieces, but we're just going to go with no for right now and say if I want to take the derivative, I'm going to need implicit differentiation. So I'm going to take the derivative of both sides with respect to x. So the derivative of x cubed is going to be 3x squared. And the derivative of y cubed is going to be 3y squared dy dx. Anytime you take a derivative of y, you're technically doing a chain rule, and you're going to leave behind dy dx. Now, when I come over here to 6xy, this is a product. So I need to use the product rule now. I'm going to call 6x the first part of the product and y the second part. So when I go to do the first times the derivative of the second, the derivative of y is 1 dy dx, because I took the derivative of a y. So the first times the derivative of the second, plus the second times the derivative of the first, and the derivative of 6x is 6. I don't need a dy dx here because I didn't take the derivative of y the second time around. All right, so I have, let's see, 3x squared plus 3y squared dy dx equals 6x dy dx plus 6y. All right. Now, step 2 says get dy dx on one side and everything else on the other side. So I'm going to have 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. Now I'm going to factor out dy dx so that I can solve for it. 3y squared minus 6x equals 6y minus 3x squared. To solve for dy dx, I have to divide by this parenthesis thing. I'm running out of space, so I'm going to put it over here. And long story short, dy dx equals 6y minus 3x squared over 3y squared minus 6x. Now, you don't have to simplify it. It's kind of begging you, if you will, to simplify and pull out those 3's. So I have 2y minus x squared over y squared minus 2x if I divide the top and the bottom by 3. Again, you don't have to do that, but it kind of really is easy to do, so we might as well do it. There's my derivative. All right, now it says write an equation of the line tangent to the graph at 4/3, 8/3. So I have the point. Now I need to plug this into the derivative. Ugh. All right, well, I got to do it. So I'm going to plug 4/3, 8/3 into this derivative. There's a reason to simplify. I'm dealing with 2's and 1's and not 6's and 3's. So if I want the derivative at 4/3, 8/3, I'm going to have 2 times 8/3. Yes, you should be able to do this without your calculator. Minus 4/3 squared over what? Y squared, which is 8/3 squared, minus 2 times 4/3. 16/3 minus 16/9 over 64/9 minus 8/3. All right, this is a complex fraction. I'm going to go through and multiply the top and the bottom by 9, because my life will get easier if I do that, which is going to make this, well, 3 goes into 9 3 times, so really a 3 times 16 is 48, minus 16 on top. On the bottom, I have 64 minus 24. 48 minus 16 is 32. 64 minus 24 is 40. 32/40 will quickly become 4/5. So there's my slope. There's my point. The tangent line would be y minus y1 equals mx minus x1. And there's my tangent line. So now we need to write horizontal line equations. Find the two equations for the horizontal lines that are tangent to the graph. Now, because I can see it here, I'm going to come up here and kind of sketch it. I have a horizontal tangent about here, and I have a horizontal tangent that looks like it's 0 here. But I want to calculate exactly what those line equations are. So if I have a horizontal tangent line, that means that the derivative has to equal 0, because then I'll have a slope of 0. So I have 2y minus x squared over y squared minus 2x, and I need that to equal 0 in order to have a horizontal tangent line. And if a fraction equals 0, that means the top equals 0, so 2y has to equal x squared. Set this equal to 0, add the x squared. And then y equals x squared over 2. So when this happens, I'm going to have my horizontal tangent lines. All right, well, that really means, in a couple different ways, this really means that this has to happen in the derivative, but it has to also be a point on the original equation. So anytime y equals x squared and x and y have this relationship, I'm going to have horizontal tangent lines. Okay, fine. Well, if this equation needs to happen at the same time as this equation, that's really a system. And x cubed plus y cubed has to equal 6xy, which in our case is y cubed is going to be x squared over 2 cubed, and 6xy, x squared over 2. I substituted this y in for the other one, and that happens a lot with implicit relationships, because you have these functions of x and y and x and y and x and y, and they happen succinctly, so you need to kind of substitute one into the other to find the values that you really need. So long story short, I want to solve this equation, which looks nasty, but it's not nearly as nasty as you think. So I have x cubed plus x to the 6th over 8 equals 6x cubed over 2. And if I set this equal to 0, I'm going to have x to the 6th over 8 minus 2x cubed equals 0. I can solve that. That's not too bad. I'm going to pull out a 1/8 x to the 3rd, which I know is going to freak you out. But if I pull out 1/8 x to the 3rd, this is going to be x cubed minus, and then this is going to be 16 equals 0 there. And I know that looks weird, but basically 1/8 distributed gives me that x to the 6th over 8. 1/8 over here, 1/8 of 16 is -2. So it works out fine. And then my answers are x equals 0 and x equals the cube root of 16. So there's my two values for x that give me horizontal tangents, but if I want the equations of the horizontal tangents, I need the y values for those. So I can plug these back into here, and I can say, all right, when x equals 0, well, y equals 0. And when x equals the cube root of 16, and I square it and put it over 2, then I get, let's see, 16 to the 2/3 over 2. If I want to write it like that, I can, or I can write it as, let's see, that would be 16 times the cube root of 16 again. Ugh. I don't know. I don't want to worry about that. So we'll just leave it 16 as 16 to the 2/3. Not to mention this one I just said was wrong, so ignore what I said there. Here's my two y values. Well, these are y values. They're also horizontal lines. So y equals 0 and y equals 16 to the 2/3 over 2 are the two horizontal lines tangent to the graph. Now, it doesn't affect it here, but in other implicit relationships, sometimes what we find is we get extraneous solutions. So one of the other things you want to do in a case like this, when you're using a system to solve, is you want to make sure that the answers you got also satisfy the original equation. So I had x cubed plus y cubed equals 6xy. I just want to make sure that these are points on that graph. So does 0 plus 0 equal 6 times 0 times 0? Yeah. So this set is fine. All right, now x cubed plus y cubed. So x equaled the cube root of 16, so that would just be 16. Y was 16 to the 2/3 over 2, so that's cubed really going to be like 16 squared over 8 equals 6 times x times y, and x is 16 to the 1/3, and y is 16 to the 2/3 over 2. All right, so let's see. 16 squared over 8. Let's pretend I don't have a calculator because I don't feel like pulling one up. This is going to be 16 times 16 over 8. 8 goes into 16 twice. So 16 plus 16 times 2 is 16 times 3, which is 48. 16 to the 1/3 times 16 to the 2/3 is 16 to the 1st. 2 goes into 6 3 times. So I have 3 times a grand total of 16 to the 1st, which is 48. That works also. So these are both points on the original were covered. Again, it didn't matter here, but in many, many cases you get an extraneous solution, and the only way to check is to see if x and y both go into the original. I'd like you to do example 3 on your own, and then we're going to stop there. We're going to do example 4 in class because this video is getting pretty long, and I think it's worth pausing to do a little bit on your own. So take a second, do this derivative on your own, and then we'll come back and talk about it. Look, it magically appeared. So when we go to take the derivative of 4x squared is 8x, y squared 2y dy dx. Negative 8x becomes negative 8, plus 4y becomes 4 dy dx. Don't forget that dy dx. Anytime you take the derivative of a y, leave behind dy dx. 4 became 0, 0 stayed 0. Then I solve for dy dx. I basically factored the dy dx out here, had 2y plus 4, moved everything else to the right, divided by 2y plus 4, and then I got my derivative, which I've got over here. Now, the next question says, find out when it has a vertical tangent line. Well, a vertical tangent line means slope is undefined. Slope is undefined when the bottom equals 0. The bottom equals 0 when y plus 2 equals 0, so y equals negative 2. It says find the points, indicating find the coordinates of the points. So the next thing I did is I plugged that thing back into the original, right about here. Got x equals 0 and 2. So the points are 0, negative 2, and 2, negative 2. Will give you a vertical tangent line. All right, I think that covers it.